Hello everyone, this is Babitha, working as Assistant Professor in the Department of EC in Institute of Aeronautical Engineering. So in this session, I'm going to discuss about different characteristics of operational amplifier and also the different configurations of the operational amplifier. So while coming to the contents, in this session, I'm going to discuss about what is meant by operational amplifier. Actually, we discussed this one in the previous session. Just I'll revise what is meant by it and why we are moving for this operational amplifier and characteristics of operational amplifier and about virtual ground concept and how we are going to utilize that virtual ground concept in the different configurations of the operational amplifier. So before going to the analysis part of the operational amplifier, first of all, we have to know what is meant by operational amplifier and why we are moving for this operational amplifier even though we are having the normal single stage amplifier. See, in the case of operational amplifier, the name itself indicating it is going to perform some mathematical operations like addition, subtraction, integration, differentiation, etc. So these kind of operations we can able to perform by using the operational amplifier along with the amplification. The normal amplifiers, they can able to amplify the applied input signal, but in the case of operational amplifier, along with the amplification, it can able to perform the different mathematical operations, and also along with this, it can able to generate the waveforms also, different kind of waveforms. That may be the sinusoidal waveforms or non-sinusoidal waveforms. So along with the mathematical operations, it can also able to generate the waveforms. That particular waveforms we can utilize in order to verify the functionality of any device, whatever we are designing. So now we will see in the case of amplifier, we are providing some signal, input signal. So the function of this amplifier is to amplify the applied input signal. So that we will get in the form of output. So this output is the amplified version of the input signal. That is nothing but the amplitude of that particular applied signal is increasing here. In some cases, the characteristics of that particular signal, that may be the frequency and phase, are also varying along with the different modulation techniques. Okay, so here in the case of this amplifier circuit, it can able to provide some extent of voltage gain as well as current gain, and along with that, it can also provide some input impedance as well as output impedance. But these parameters coming from this particular single stage amplifier in some cases cannot be able to run some practical applications. So these are not sufficient to run some practical applications. So that's why in order to overcome this particular problem in the single stage amplifier, we are moving for the multi-stage amplifier. So what is mean by this multi-stage amplifier? See, multi-stage amplifier is the cascading of two or more number of single stage amplifiers. Why we are moving for this multi-stage amplifier means in order to improve the parameters of amplifier here. So if we improve these parameters, we can able to utilize for all the kind of practical applications. Even though this single stage amplifier also can able to run some applications only, some low frequency range of applications only, this can able to run here. But if you wanted to run all kind of devices, all kind of frequency signals, we have to go for the multi-stage amplifier. In the case of multi-stage amplifier also, these are able to improve these parameters of the amplifier. These are increasing all these parameters. So different type of multi-stage amplifiers can able to improve different parameters. Some multi-stage amplifiers can able to improve the voltage gain. In some cases, they may able to increase the current gain. In some cases, they may decrease the output resistance. In some cases, they may increase the input resistance of the amplifier. So depends upon our requirement, we can able to choose any one of the multi-stage amplifier. But even though in this case also it can able to amplify the signals only in the range of mid frequency only. So those can able to provide the stable gain for the for the medium frequency range of signals only. For the low frequencies as well as for the high frequency range of signals, it will provide the attenuation. It is providing the attenuation means those are decreasing the quantity of the gain in the low and high frequency range of signals. Those can able to provide the constant and stable gain in the mid frequency range of signals only. So that is the specialty of the multi-stage amplifiers. So these normal amplifiers can able to amplify the low frequency signals, and this multi-stage amplifier can able to amplify the mid frequency range of signals. But what about high frequency range of signals? So in order to amplify all range of frequency signals from 0 to some megahertz signals, some low frequencies to high frequency range of signals, we are moving for the differential amplifier. So what is the basic difference between the multi-stage amplifier and this differential amplifier here? In the case of multi-stage amplifiers, we are interconnecting the different number of single stage amplifiers. In the case of differential amplifier, we are taking the two identical transistors. Two identical transistors in the sense those are having same characteristics in all the way. And they are we need to provide the biasing conditions also same for both the transistors. And also the collector resistances as well as emitter resistances of both the transistors are also must be equal. So in that condition, we have to choose two transistors to design the differential amplifier. So what is the basic function it can provide here? It is here in this case we are using two transistors means we are providing two inputs, V1 for the first transistor and V2 for the second transistor. So this differential amplifier will take the difference of these two applied input voltages V1 and V2. So the differential voltage it will amplify here. So instead of amplifying the applied input signal, it can able to amplify both the signals difference. So that is the specialty of the differential amplifier here, and this can able to provide very high gain compared to the single stage as well as multi-stage amplifiers, and this can able to amplify all range of frequency signals. So because of this reason only, this differential amplifier we are utilizing in the case of operational amplifier. So to design the operational amplifier in all the internal stages, we are using the different types of differential amplifiers. So what type of differential amplifiers we are having here? So four types of differential amplifiers are there. Those are dual input balanced output differential amplifier and dual input unbalanced output differential amplifier, single input balanced output differential amplifier, and single input unbalanced output differential amplifier is there. So among these four configurations in the operational amplifier, we are utilizing these three. These three configurations we are utilizing in the internal stages of operational amplifier. So these are having four configurations, but the analysis part and the operation of all the four types of differential amplifiers are same. But the only difference is how many number of inputs we are providing for the differential amplifier, whether we are providing the single input or two inputs, or whether we are taking the output common between the two collectors of the two transistors, or else we are taking across the single transistor collector. So depends upon that only. These are dividing into four categories, but the operation point of view and the analysis point of view, these all are same. So in the case of operational amplifier, because of utilizing this differential amplifier characteristics, it can able to improve still more gain parameters of the amplifier, that may be the voltage gain or current gain, and this can able to amplify AC signals as well as DC signals, both the kind of signals it can able to amplify here, and along with this it can able to perform all the mathematical operations. So these operational amplifiers previously designed with the vacuum tubes, and those size also very high, and cost is also very high, and those are very complex. But nowadays this operational amplifier is available in the form of IC 741 IC form. So the function of this 741 operational amplifier is to amplify all the kind of signals, and in this 7 is nothing but the 7 functional pins are there. So in that 4 are utilizing for the inputs and 1 is for the output here. So that's why it is named as 741 operational amplifier, and it is having total 8 pins. So now we will see, we are talking about the IC. Actually, what is mean by this IC? Why we are moving for this IC concept means our operational amplifier nowadays it is available in the IC form. So that's why we are moving for the what is meant by IC here. IC is nothing but the integrated circuit, and it is the very small chip or very small device, and the cost of this one also very less, and this is also one of the electronic circuit here. Okay, IC also it is in small size, and it is also some electronic device. And what it consists of means, it consists of all the active elements as well as passive elements, that is active as well as passive components are integrated on the single wafer or single material, so that we can call it as the integrated circuit. So here we are telling that active and passive components. What are that active components and what are the passive components? Here we may take active components are transistors, diodes, and operational amplifier also we can take, and passive elements are resistors and capacitors and inductors. We can call it as the passive components. So in the case of active components means they can able to generate the source or energy from itself. But in the case of passive components, in order to operate that particular component, we need to provide external energy here. So those are the passive components. So in the designing of IC, we can able to integrate all the kinds of passive elements as well as active elements. So in the 741 operational amplifier also, we may have all the active as well as passive elements. Or else we can also call it as chip or microchip. It is a semiconductor wafer. Why we are calling it as a semiconductor wafer means, on this single small piece of semiconductor material, we can able to integrate so many number of components. So that's why it is called a semiconductor wafer, on which thousands or millions of tiny resistors, capacitors and transistors and MOSFETs we can able to fabricate here. So the combination of all these will define any one of the application here. Suppose I wanted to design some adder means, what are the elements required for that adder? We have to integrate on this particular chip. Or else by using the 741 operational amplifier, we can able to get that particular application by connecting different resistors and capacitors and by using wires. And what are the advantages of IC and why we are moving for this IC even though we are having the normal components here? The thing is the compact size. See, in the case of 741 operational amplifier only, in the previous cases we are having with the vacuum tubes. So the size of vacuum tubes was very bulky here. So but if you implement by using in the form of IC means, the size will be reduces here. And also weight is very less. Vacuum tubes means the weight of that one is very high, but IC is in very small size and small weight. And the power consumption, when coming to the power consumption also, in the form of IC it is there means just we can apply some kind of ICs we can able to run by using only 5 volts. But in the case of 741 operational amplifier, we need to provide some minus 12 volts to plus 12 volts range of voltage here. And reduced cost. Cost is also very less. ICs are available with the small cost compared to the vacuum tube based devices. And while coming to the reliability, in the accuracy of the results also, ICs can give directly the final result. But in the case of a normal circuit implemented on the breadboard or any other, they may give the value incorrect due to any temperature variations or parameter variations or component variations, or due to the age factor. They may give the result in incorrect manner. But in the case of ICs, it can give reliable output or accuracy of the output. And speed is also, we will get very high in the case of ICs instead of normal circuits. And while coming to the applications of IC, these particular ICs we can utilize for different types of applications. That may be for the amplification, to amplify the signal, and that may be for the oscillator to generate the waveforms, and timer to generate the timing waveform, and counter to run different types of microprocessors and microcontrollers. And to design the computer memory also we can utilize these ICs, and to design microprocessor we can utilize this, and to design any microcontroller also we can utilize this. These are some few examples I am indicating here. So many applications we can design. Nowadays everything is designing in the form of ICs only. So while coming to the 741 operational amplifier, what is the symbol of that 741 operational amplifier? So in the symbol we are taking 5 terminals here. So in that 5 terminals, 2 are the input terminals. This is plus indicates the non-inverting terminal of the operational amplifier, and minus indicates the inverting terminal of the operational amplifier. Okay, so this we are indicating with the V plus and V minus, and this is the second pin and this is the third pin in the case of 741 IC. And this Vs plus is nothing but the plus VCC, that is nothing but a positive supply voltage. And this Vs minus is nothing but a minus VEE. This is the collector voltage and this is the emitter voltage, and it is in the positive and it is in the negative. So this is negative supply for the emitter terminals of the internal differential amplifiers of the operational amplifier. And this one is the Vout, that is the output voltage we are measuring here. And this is the 6th pin, this is 7th pin, and this is 4th pin. So among the 8 pins of the operational amplifier, always we are going to utilize 2, 3, 4, 6 and 7 pins only. Remaining 3 pins are not connected or unused pins here. Okay, and we can also represent this one in this way. So with the triangle with 2 input terminals and 2 supply voltages and 1 output indicates the symbol of the 741 operational amplifier, and it is very important that the symbol of the 741 operational amplifier and what are the pins indicating that symbol is very important. Why? Because if you know that a particular number of that particular symbol and the function of that particular pin, then only we can able to implement any kind of application here by using this operational amplifier. And now we'll see what are the different characteristics of operational amplifier. So while coming to this particular characteristics, these are different in the case of ideal operational amplifier and in the case of practical operational amplifier. So why I am telling these are different in both the cases means, in the ideal case all the values we will get it as accurate values, means we are assuming that we need to achieve that particular value, that may be the extreme infinity or that may be the 0 value. So we, in the case of ideal case, we will indicate either directly 0 or infinity. But in the case of practical applications, not only the operational amplifier, any kind of circuit, we cannot see the practical case how much we can able to get. In this case, this 0 value we may not get it as exactly 0 here. That's why we will indicate with some small value. So less than the 0 also we may get, or more than the 0 also we may get. That is depends upon the circuit here. And while coming to the infinity also, we cannot say it is directly the infinity in the practical case. We may get it as some large value here. So these characteristics will vary with the ideal case as in the practical case. So what are the different types of characteristics are there? So first one is the output offset voltage, and next input bias current of the operational amplifier, and input offset current, input offset voltage, and slew rate. And along with this, we are going to discuss the gain bandwidth product of the operational amplifier. So now we will see about this each and every parameter or characteristics. So the first characteristics, here it is the output offset voltage. So what is meant by this output offset voltage? So the voltage which is present at the output of the operational amplifier whenever the two input voltages are zero, that is differential voltage is zero, is nothing but the output offset voltage. That is nothing but differential input voltage. We are not providing anything. Here differential input voltage is zero means both the input terminals of the operational amplifier are zeros. We are not providing anything. So VD is nothing but here V1 minus V2. So this voltage is zero means, this differential voltage is zero means, in the ideal case, the output voltage should also get zero. But in the practical operational amplifier, even though we are providing this differential voltage is zero, we are not able to get this value as zero here. We are getting some amount of value here. So that particular voltage, we are calling it as output offset voltage. Here what is mean by offset here? Offset is nothing but there is no input. Okay, the circuit is in offset condition means we are not at all providing any input for that particular circuit. So in the ideal case, if we are not providing any input means we should not get any output. But in the practical case, due to the component variations or due to any parameter variation, we are getting some particular output voltage. So that particular voltage we are calling it as output offset voltage. So this one we can indicating in the op amp. So the voltage for this one, we are giving here it as V1 and V2. The output is V0. So these two, in between these two is the differential voltage. So this must be 0 here, but in the practical case, we are not getting it as 0. And next characteristics is the input bias current. So what is mean by this input bias current here? So input bias current we are indicating with the IB here. Input bias current we are indicating with the IB here. So what it indicates, it is the average of the currents which are entering into the two input terminals of the operational amplifier. That is nothing but how much amount of current which is flowing in the non-inverting terminal as well as how much amount of current which is flowing in the inverting terminal of the operational amplifier. So this one we can also indicate in the closed loop fashion. What is mean by open loop and closed loop? We will see it in the later slides. So for now, input bias current is the average of both the currents which are entering into the two terminals of the operational amplifier. See here, IB plus is the current which is flowing in the non-inverting terminal or third pin. IB minus is the current which is flowing in the inverting terminal or in the second pin of the operational amplifier. So that one only we are taking here IB plus IB minus divided by 2 is the input bias current of the operational amplifier. So this is the open loop case. We are not at all providing any feedback from output to input here. And similarly, if we are providing the feedback from output to input means it will be in the closed loop form. So in that case also, this same formula is applicable. So in the ideal case, this value should be 0. Whenever the differential voltage is 0 means this value should be 0. But in the practical case, in the 741 operational amplifier, this bias current, input bias current is 500 nanoamperes. And next one is input offset current. So this input offset current we are indicating with IIO, capital I, subscript small IO, input offset. This input offset is nothing but this is the difference between the currents which are entering into the inverting as well as non-inverting terminals of the balanced amplifier or operational amplifier. So in this case, we are taking the difference of the two currents which are entering into the two terminals of the operational amplifier. So where here IB1 is the current which is entering into the non-inverting terminal, and IB2 is the current which is entering into the inverting terminal, and this is the difference of the two currents flowing into the two terminals. So in the ideal case, obviously this value is 0, but in the practical case, in the case of 741 IC, this value is 200 nanoamperes. So in this case also offset, we are indicating offset means we are not providing any input voltage. There is nothing but two input voltages are 0, so the differential voltage is also 0. That is nothing but though we are not providing any differential input voltage also, it is providing some input current. In the previous case, though we are not providing any input voltage also, it is providing some output current. And next one is input offset voltage. So I have already mentioned in the operational amplifier, when we are not providing any input voltage means the output should be 0 here. Okay, in the ideal case, the output should be 0 here. So in this condition, the practical op-amp will show some amount of value here. In the ideal case, V0 is 0, but in the practical case, this value is not 0. V0 is some value we will get here. So why we are getting, even though we are not providing any input voltage, also why it is providing some output voltage means that is due to the mismatching present in the internal circuit of the operational amplifier. So this particular input offset voltage will give the error in the practical applications. That is nothing but if that particular operational amplifier which is having some input offset voltage, that particular operational amplifier only we are utilizing for the practical applications means we will get the output as some error value. We will not get some accurate value here. So to make such particular input offset voltage is 0 because that is not desirable here. So to make it as that 0, we are applying some external, some difference voltage between the two input terminals of the operational amplifier. So that particular voltage we are calling it as input offset voltage. We are offsetting the input signals should not provide the output voltage. So what is that input offset voltage we are providing here? It is defined as the differential voltage that must be applied between the two input terminals of the operational amplifier in order to nullify the output voltage whenever the input is 0. So that is nothing but we are indicating with VDC1 and VDC2 that we are applying to the non-inverting terminal as well as inverting terminal of the operational amplifier in order to make your output voltage as 0 or in order to nullify the input offset voltage. So the formula for this one is this one, VDC1 minus VDC2. And next one is the slew rate here. The slew rate of any device or operational amplifier indicates the what is the maximum rate of change of output voltage with respect to time. That indicates the slew rate of any device here. So in this case or any devices, it is specified in volts per microseconds. That is nothing but how much output voltage with respect to time it is changing. And it is also given by S equal to dV naught by dt, the variation of the output voltage with respect to time. So that one we are indicating with the differentiation. And we can also indicate with current by capacitance of that particular device. So the slew rate of any device indicates that how much fast that particular system or device is responding whenever we are providing the input signal or whenever the input signal is changing. So it is specified by operating in the operational amplifier. It is specifying in the unity gain condition. So if input is instantly changing like a square wave means, then for unity gain, output must also should change instantly. But in the practical case, we may not change like that. Why? Because it will take some time to respond. But in the ideal case, at that instant, whenever we are providing the input signal, at that instant only it should provide the output. Okay. So this slew rate is caused due to the limited charging rate of the compensating capacitor, as well as current limiting saturation, and as well as the internal stages of the operational amplifier. And this is occurred whenever the high frequency large amplitude signal is applied to the operational amplifier. So the internal capacitor voltage cannot change instantaneously. Capacitor will not respond instantaneously whenever we are providing the voltage to that. It will take some time to charge or to store the electric charge in that. So that's why we are indicating with dVc by dt equal to I by C. So for large charging rate, the capacitor should be very small and the charging current should be very large in order to get the proper speed in the circuit. So for large charging rate, the capacitor should be small or the current should be also small here. So the slew rate of the op-amp is depends on the maximum internal capacitance or maximum internal charging of the circuit. So that's why we are writing it as S equal to I maximum divided by capacitance of that circuit. So that indicates the slew rate here. So now we will see the one example on this calculation of slew rate. For IC741, the charging current is 15 microamperes. So the current given it is, the maximum charging current given it is 15 microamperes. And the internal capacitor value is 30 picofarads. And what is its slew rate? Slew rate formula is, this one is equal to I maximum divided by capacitance. So that's why 15 into 10 power minus 6 divided by 30 into 10 power minus 12. So if we calculate this, we will get it as slew rate as 0.5 volts per microseconds. And next parameter is the gain bandwidth product. And this is the major characteristics in order to design the operational amplifier here. So the op-amp gain bandwidth product is defined from the open loop configuration as well as from the output load of the operational amplifier. So here gain bandwidth product is nothing but the gain. Gain is voltage gain AV, and bandwidth is nothing but the frequency range of that particular operational amplifier. So that's why it is AV into F, where GB is the op-amp gain bandwidth product, AV is the voltage gain, F is the cutoff frequency of that particular operational amplifier. So in the case of 741 operational amplifier, the gain bandwidth product is, or cutoff frequency is 1 MHz here. So this value, gain bandwidth product, is constant for voltage feedback amplifiers of the operational amplifier. So here the gain value is decreasing means the bandwidth also increases by the same factor here. So these are all the characteristics of the operational amplifier. And next we'll go with the virtual ground concept. And why we are discussing this virtual ground concept? Why? Because means this virtual ground concept we are going to utilize in the open loop as well as closed loop configurations of the operational amplifier. Actually, what is meant by this virtual ground? I have already mentioned, whenever the differential voltage, in the ideal case of operational amplifier, always the differential voltage must be 0 here. That is nothing but whenever it is 0 means both the inverting as well as non-inverting terminals is also essentially must be 0 here. So this is obvious because if the output voltage is some few volts, we are taking some output voltage is few volts. So, and the gain which is provided from the amplifier is high. I am taking the output voltage is less, but the gain is very high. In that case, the differential voltage we need to get must be 0 here. Output is large value, output is some small value, gain is some large value. So in these two conditions, we need to get the differential voltage must be small value. Almost we need to get it as 0 in the ideal case, but in the practical case, we will get some small value. So I can explain this one with one example. Here output voltage I am taking here it as 10 volts, and the open loop gain I am taking here it as 10 power 4. So in this case, my output voltage of any amplifier is the gain times the applied input voltage. So that's why AOL into VD here. So from this I want the VD parameter here. Why? Because we are discussing about the differential voltage. So VD is nothing but V0 by open loop gain, that is 10 by 10 power 4. That is nothing but 1 millivolts. So 1 millivolts means this value is very, very small. So in this case, if I am increasing my open loop voltage to infinity value means definitely the differential voltage must be goes to 0 value here. So that's why in the analyzing the circuits, we are assuming it as this differential voltage is 0 even though it is providing some small voltage. So if we are making this differential voltage is 0 means we will get it as, here VD is nothing but V1 minus V2. If VD equal to 0 means what we will get? V1 is equal to V2. So both we will get it as equal here. That is nothing but from this virtual ground concept we can say in the operational amplifier, one terminal is at one particular voltage. The second terminal is also at with that same particular voltage. That may be some voltage is present or that may be the ground here. If it is one terminal is grounded means due to the virtual ground concept, second terminal should also act like a ground. If one terminal is having some voltage means second terminal should also having some same particular voltage. So that is the concept of the virtual ground that is coming due to this differential voltage is 0. So in this case, there is no current flows from the input terminals to the ground here. Suppose if the non-inverting terminal is grounded means by the concept of virtual short or virtual ground effect, the inverting terminal is also acts like a ground potential. So there is no physical connection between the inverting and non-inverting terminal, even though those are acts like with the same ground or some same potential across both the terminals. So this is the principle of the virtual ground. So this particular concept we are applying for the configurations of the operational amplifier. So now we will move with the configurations of the operational amplifier. So any operational amplifier is available in two configurations, that is open loop configuration as well as closed loop configuration. So what is mean by this open loop configuration? In the case of open loop configuration, the output of the operational amplifier is always depends upon the present how much input voltage we are applying. It is not depends upon or it is not affecting on the any other parameters. So that we can call it as the open loop configuration. So in this case, we are not providing any feedback from output to input and we are not giving any some part of the output voltage to the input here. So in this case, the operational amplifier will provide the very high gain. And in the open loop configuration, the op-amp will operate in three configurations. That is the differential amplifier, inverting amplifier and non-inverting amplifier. About this differential amplifier already we have discussed in the first slide as well as in the previous sessions also we have discussed. The differential amplifier will amplify the applied differential voltage whatever we are applying across the two input terminals of the differential amplifier. And now we are going to see the inverting and non-inverting amplifiers. So in the inverting amplifier, first I am going with the open loop configuration. Actually, why it is called as inverting amplifier? When we are providing the input for the inverting terminal of the operational amplifier and non-inverting terminal is grounded, so that we can say it as the inverting amplifier. And why it is called as open loop means we are not connecting any output signal back to the input. So that's why it is open loop inverting amplifier. So that's why in the circuit also we are mentioning here positive terminal or non-inverting terminal is grounded here. For the inverting terminal only, we are providing the input signal. And this load resistance is measure the output voltage. So how much voltage I will get here? So actually in the operational amplifier internal, all circuits are differential amplifiers. So in the case of differential amplifier, the input voltage is VD, and this VD is nothing but V1 minus V2. Okay. And here in this case, my V1 value is 0 and V2 value is Vi we are providing. Okay, so now substitute this V1, V2 in the VD. VD equal to what we will get here? 0 minus Vn. So VD is nothing but what? Minus Vn. So what is the input voltage we are providing here? Minus Vi voltage we are providing for the amplifier. And what is my output voltage? I can expect here it is output voltage is gain times the input voltage. So in this case, my input voltage is minus Vi. So that's why minus A into Vi. So in the case of inverting amplifier, it will amplify the applied input signal with phase shift of 180 degrees. This minus symbol indicates the 180 degrees phase shift between the applied input signal and what is the output we are getting here. Along with this phase shift, it can also amplify the applied signal. So this is the open loop case of the inverting amplifier. The output voltage is V0 equal to minus A into Vi. It is very important to solve the problems. And next we will see the closed loop configuration of the operational amplifier. So what is meant by closed loop here? Whenever some fraction of output voltage or output signal we are taking and we are connecting back to the input means that is the closed loop configuration of the operational amplifier. So this is the closed loop configuration of the operational amplifier, and here inverting amplifier. So that's why again we are providing the input for the inverting amplifier, and the feedback we are giving back from output to input through the feedback resistance RF. So in this case, how much output voltage we will get? That is minus RF by Rn into Va. And the gain is minus RF by Rn here. So this particular amplifier, we can call it as the closed loop inverting amplifier, and which uses the negative feedback to control the overall gain of the amplifier. Why we are calling it as a negative feedback here means we are providing the feedback to the inverting terminal. So that's why it is negative feedback. We may utilize the positive feedback also. So now we will see how this gain is coming from this particular circuit. So for that purpose, I am considering the same circuit here, closed loop inverting amplifier. In that, I am taking what are the elements which are connected to the inverting terminal and what are the elements which are connected to the non-inverting terminal. So that is the first step. First I am taking the inverting terminal and non-inverting terminal here. For the inverting terminal, two resistances are connected, Rin as well as Rf, and that is between the Vin and Vout. So that's why the total thing I have considered here. And in the case of non-inverting terminal, it is grounded. So that's why I have indicating with the ground here. So now I want to apply the virtual ground concept here. So due to the virtual ground effect, here the non-inverting terminal is grounded means this point also acts like a ground here. So there is no connection from this R into this operational amplifier. Why? Because due to the virtual ground, this terminal also grounded here. So the current will be flowing in this path now, not into the operational amplifier. So the total current, if I calculate in the inverting terminal, is I equal to V by R. So here what is my V here? V is nothing but V in minus V out. Sorry, V in minus VB from here to here. V in minus VB by R in this drop, and that is also equal to VB minus V naught by RF. Okay, so here VA, this value is VA and this value is VB. VA equal to 0 here. So if VA equal to 0 means obviously VB also 0 due to the virtual short effect. So here VA, VB both are zeros means in this we will get it as V in by Rn, and from this we will get it as minus V out by Rf. So from this relation, if we write V out by V in, we will get it as minus Rf by Rn. That is nothing but the closed loop gain of the inverting operational amplifier is minus Rf by Rn. And here this minus sign indicates the 180 degrees phase shift between the input and output. That may be the open loop configuration or closed loop configuration. In the case of inverting amplifier, we will get the 180 degrees phase shift. And this formula also very important to solve the problems. And next we will see the non-inverting amplifier. So non-inverting amplifier means for the operational amplifier, we are going to provide the input or Vi to the non-inverting terminal, and inverting terminal is grounded here. So in this case, what is my differential voltage? Always differential voltage is V1 minus V2, the current into the first terminal as well as second terminal, voltage. And in this case, my V1 value is minus Vi, plus Vi. Why? Because we are connecting for the non-inverting terminal. And V2 value is 0. This is V1, V2. So what is my differential voltage? Vi. And what is my gain in this case? Output voltage is gain times the input voltage. So input voltage is the differential voltage here. So V0 equal to AOL into input voltage. So in the case of non-inverting open loop operational amplifier, output voltage is gain times the applied input voltage. In this case, there is no phase shift between the input and output. So while coming to the non-inverting amplifier, non-inverting closed loop amplifier. In this case, we are providing the feedback to the inverting terminal only. But the thing is, we are giving the input for the positive terminal, that is non-inverting terminal. So that's why it is non-inverting closed loop amplifier. So in this particular case, the output voltage is 1 plus Rf by Rg times the input voltage. So now we will see how we got this particular gain as well as output voltage in the closed loop non-inverting amplifier. So for that purpose, again, I am taking the elements which are connected to the non-inverting terminal as well as in the inverting terminal. Okay, so for the non-inverting terminal, the input voltage is connected. That one we are taking it as Va. And for the inverting terminal, two resistances are connected, Rg as well as Rf. So that one I have taken as it is. So this point I am taking here it as Vb. Okay. So the value of Va here it is Vn. So that's why I have written directly. And the value of Vb, by using the voltage division rule, we have to calculate this. That is, opposite resistance is Rg divided by total resistance Rf plus Rg into opposite voltage, that is Vout. So this much. So here in this case, due to the virtual ground concept, what is Va? That is equivalent to Vb here. Va equal to Vb. If that is the case, we will get it as, and again Va is equal to Vb. And but what is my Va here? Vn. That is nothing but Va equal to Vb equal to Vn. So I am replacing my Vb with Vin here. So Rg by Rf plus Rg into Vout is as it is. So from this relation, if I write output voltage by input voltage, that is Rf plus Rg by Rg. So if we simplify this, we will get it as 1 plus Rf by Rg. So in the case of closed loop non-inverting amplifier, the gain is 1 plus Rf by Rg. So this formula also very important in order to solve the problems. Okay. In this session, we have discussed about what is meant by operational amplifier and what are the different characteristics of the differential amplifier, and virtual ground concept, and how we are applying that virtual ground concept in the configurations of the operational amplifier. And along with that, we have also discussed about open loop as well as closed loop configurations of the operational amplifier. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.